So curious, huh? You want to know where that bifurcation value is, right? Because that'll tell you how many fish you can take from the pot without spoiling the whole pond. So let's go back to that logistic model with harvesting and let's locate the bifurcation value. There's a couple different ways to do this, and I'm going to start with a classic way, which reasons that the bifurcation we just talked about is a place where we used to have two roots and now we have zero roots, right? So remember that the roots, which represent the equilibrium points, are the places where this equation is equal to zero. So if we could just write an expression that solves for the values of x, where dx dt is equal to zero, we will probably be able to observe the place where that goes from having two answers to just for a minute having one answer and then vanishes. Then all of a sudden there's no real numbers that answer that question. Okay? So I want to set this model equal to zero to locate the equilibrium algebraically. And because I'm observing that it is quadratic, it's a second order polynomial in nature, what I'm going to do is I'm going to factor it through. So here you see me factoring the Rx through the other terms like that. And then I'm going to reorder it so that I can kind of see the classical quadratic form a times x squared plus b times x plus c, where the plus c here is equal to minus c. Okay, so now I've got it set up in a format in which I can apply the quadratic formula. I'll let you go ahead and look up a review video of that separately if you want to get reminded of what it is. But I'm taking the coefficients that I laid out here and I'm plugging them into the quadratic formula, which is the same thing as saying, hey, where are the places where dx dt is equal to zero? Answer, right here, at these x star right here. Remember, the quadratic formula gives us the places where a quadratic will be equal to zero, okay? And it goes like this, negative b plus or minus b squared minus 4 times a times c, all divided by 2 times a. Okay, so I just put it all in there and just looking at it and I'm like, aha, I totally see it. Maybe not yet. Let me look at it a little more. This is a pretty complicated form, but what I really wanted to know is when is my system going to go through that qualitative change that we're calling a bifurcation? And the description of that qualitative change is that there used to be two roots, and then when I pulled the parabola down enough, there was zero roots anymore. And you can see that the quadratic formula wants to give me two roots. It's going to give me this stuff plus or minus whatever the square root of this is. Now, if the stuff under the square root is a positive, then I can square root it over the real numbers, and I will get two roots because I'll be doing this stuff plus or minus whatever that square root value is. If the stuff underneath the square root is negative, I cannot take the square root of a negative number over the real numbers, and so I'm not going to have any roots. So really, where we see the qualitative change between two roots and zero roots is the same place where we see the stuff inside the square root, which is called the discriminant. We can see where does this discriminant go from being positive to negative. And just like any good continuous function, you can't go from positive to negative without going through zero. Zero is the dividing line between positive and negative values. So we're going to set the discriminant equal to zero. That's where I got this statement up here. I took this and then I just factored through the 4r over k times c to get that term right there and just combine them all. Okay, so now hopefully you know where I got this first line. It was a place where this discriminant, the stuff under the square root here, is going to be equal to zero. So it goes from being positive, two roots, to negative, no roots. And so I just need to simplify this by factoring out an r, and then look for the places where the equation will be satisfied. I'm going to divide both sides by r, knowing that r is not equal to zero. Because if r is equal to zero, it kind of messes up my whole logistic situation. It says that the population isn't growing at all. So barring the fact that r is equal to zero, I'm just going to divide through by it. And that's how I get this statement right here. Now this statement is a relationship between the three parameters, the growth rate, the carrying capacity, and the constant harvesting term. But really what I'm interested in and what I'm thinking that I have some ability to change is I get to decide how many I harvest. And so I'm going to solve this equation for C. Sure, you could solve it for R, or you could solve it for K, but what you want to ask yourself is, which one of these parameters do I really have control over? And in this case, we're considering how many fish we want to take out of the pond. And so we're going to solve this statement for C. And it tells us that when C is equal to RK over 4, that is the exact moment when our system goes from having 2 roots to 0 roots. That was a lot of algebra. I wonder who that was fun for. But let's visualize it too, so you see what I mean. So going back to the situation from the previous video, here I have illustrated what the state equation looks like in the tangent versus state space graph, where the black line represents 0 harvesting. Okay, so this is a situation where I have C is equal to 0. And in the C is equal to 0 situation, represented by the black line, I have the two equilibria, the unstable equilibrium point at 0 and the stable equilibrium point at K. But now I want to draw your attention to another part of the graph, which you may have noticed and always wondered what the significance of it was. On a down-facing parabola, we have this special point up here, known as the vertex. Okay? Now, maybe I shouldn't have marked it with a dot because it's not an equilibrium point. Okay, just to be clear about that, the equilibrium points of the system are the roots. They're the places where the function that represents dx dt is hitting 0, so that you have that equilibrium behavior. But there's this special place right up here, this peak, and I know that it has significance because if you're asking me at what point of harvesting will I have pulled this whole system down so that these two roots have come so close together that they merged, at what point is my system going to look like this? Like C is equal to what value? What value of C is going to pull down that parabola such that there's just that one single root? This is exactly the value of C at which we have a double root for the equilibrium points, and it is the same value of C that we just solved for here, because remember that the algebra told us to set the discriminant equal to 0, set this part equal to 0, and that's where you get the double root, right? And that double root is located right here when C is equal to RK over 4, okay? That is exactly the height of the parabola at its vertex if you consider the situation without harvesting. Okay, so let me just show you that because that's another way that you can see how this bifurcation is occurring. A whole separate route. I mean, sure, all this algebra was a lot of fun, but a whole separate route to locating the bifurcation value would be to simply ask yourself, what is this point on the graph? Right? What is the location of the vertex? And actually, seeing this function right here, ignoring the C, we could implement the vertex formula. Do you remember the vertex formula? Right? It's negative b over 2a. And so I could do negative b and divide it by 2a, just ignoring the c for now. And I would find via the vertex formula that the location of the vertex is exactly halfway between the two equilibrium points. It's exactly k over 2. And that is my state value. That's my value for x at which that vertex is located in the function f of x. But remember, I was wondering what the height of it would be, right? Now I know the x location of the vertex, but really I want to know the y location of the vertex because this height right here represents the maximal amount that I could harvest out per year without making it guaranteed go extinct, because that's the exact height at which I would have pulled it down to get a double root right there. So do you remember how I would get the y part of the vertex? The vertex formula in pre-calculus just gives us the x location. It just tells us for what value along the horizontal axis the vertex occurs. And then in order to get the y value, we have to plug it back into the equation. Right. So remember that the equation that I'm working with here is the place where c is equal to 0, right? So I'm just going to erase this part right here. And in order to get this height right here, I'm going to evaluate f of x, okay? So in order to get the value right here, I'm going to take this value of x and I'm going to say, well, f evaluated at the location k over 2 is equal to r times k over 2. You see I'm going back to here, and everywhere I see the x, I'm going to replace it with k over 2 because I'm evaluating f of x at that point. And then I'm going to say 1 minus, remember x is equal to k over 2 divided by k. And remember, this is the black line. This is the place where c is equal to 0. So I'm not going to put a c in there because this is the instance where I'm not considering harvesting. I just want to know what this height is because that's the most that I could harvest, and it would turn the black line into the dotted line. So if you simplify this expression up here, you're going to see that the first term simplifies to rk over 2, and the second term simplifies to 1/2. And so the eventual height that we get here is rk over 4. That sounds kind of familiar. Rk over 4. All right, that's where I got by setting the discriminant of the quadratic formula equal to 0. It's the same thing. It's just another way to get the bifurcation value. This again tells me that if I pulled this black graph down by the amount rk over 4, then I would get the dotted line. And that's the dividing line between having 2 fixed points and then on this dotted line just having 1 fixed point. And then if we pulled it down any more than that, then we would have just sadness, no more fish, no more fixed points. Okay, so that's 2 different ways that we can find the bifurcation value. But how about this? For free, I will give you one more way that you can find the bifurcation value. And I wonder which one is going to be your favorite way. This one might be mine because in practice, if you really start implementing this theory in really complicated equations, this third way is the most common way that I think is actually used to find bifurcation locations. Okay? Now for this last way, I just want to illustrate I just want to note the observation that the vertex is a very special place on this black line. Okay, maybe I should erase the sad face. It's a little bit distracting. Okay, remember how we talked about what type of derivative is visible on the tangent versus state space graph? What type of, if I was going to draw a tangent line, what would the mathematical expression be for the tangent line? Because I'm about to draw a tangent line right at the vertex, right here. I'm going to draw a tangent line that's tangent at the vertex. Okay? That happens to be a horizontal tangent line. So that happens to be a place where the slope of the tangent line would be equal to 0. But first I have to remember, what derivative am I talking about when I observe that I have that 0 tangent? Remember, derivatives are always a type of slope, and just like a normal slope, they will have the form rise over run. So the rise is f and the run is x, and so the tangent represents the derivative df, the rise, over dx, the run. Okay? When you look at this black graph of f of x, there's actually only one special place where if I drew a tangent line with my red pen, I would get exactly a horizontal tangent. Remember that df dx is usually used to classify the stability of equilibrium points. So df dx right here is positively valued. That's what told me that this is an unstable equilibrium. df dx is negatively valued over here, so that's a stable equilibrium. Now before, when I talked about linear stability theory, I said a place where df dx is equal to 0, like right here, where df dx is equal to 0, that's a place where linear stability theory would fail to conclude stable or unstable. that's still true. But looking for places where df dx equals 0 is actually another secret method for locating bifurcation values. Because when we see this graph, we see that pulling it down to the point where we would have a double root also corresponds to the value of c, where we would have that horizontal tangency right there. So if I set df dx equal to 0 and I look for the place at which that's true, that's going to give me a third method to find the bifurcation value of c. Okay, so let's check that out. This is now our third method where this is f of x. I guess I should have factored it out again because I'm going to be using the power rule. So just to factor it out again, that's what it is in its factored out form. Okay? And then I'm going to use the power rule to take the derivative, right? And so df, this is equal to f of x. df dx, according to the power rule, is take the derivative of this term rx, that's a linear term, so its derivative is r. Take the derivative of minus rx squared over k, you're going to get minus 2rx over k. Take the derivative of a constant term c, and you're just going to get 0. Okay, that's cool. So I have this as the expression for df dx, and remember, this is the same exact expression that if I had expressions for the equilibrium points, I would evaluate this at the equilibrium points and determine through the sign of it, either positive or negative, whether I had an unstable or a stable fixed point. But now I'm setting it equal to 0 to locate the bifurcation value. If I set it equal to 0, it's going to tell me what value of x am I going to have that special place where df dx is equal to 0. Ooh, so now I'm going to set it equal to 0, and I'm going to get 2rx over k is equal to r. And I'm going to solve that for x. Okay, so we're going to have x is equal to divided by r, multiply both sides by k, divide both sides by 2. X is equal to k over 2. X is equal to k over 2. X is equal to k over 2. Now I'm back where I started when I was talking about my second method using the vertex formula. All of these things are bringing you to the same place, but hopefully they're helping you understand it from different points of view. So again, to review, the method that I just went over here was I set df dx equal to 0, and it gave me a place where if this was the equilibrium point, the system would be bifurcating. And I know that because if this was the equilibrium point, if this value, x is equal to k over 2, was the value that intersected the x-axis right there, then I would be guaranteed to have horizontal tangency in df dx at that point. I would know that that's a place where linearity, the linear stability theory, would fail. And in fact, if you try to check linear stability theory here, sure enough, you see that that would be a node. That would be a semi-stable node at that point right there. And it tells me what value of the equilibrium point x at which the bifurcation would occur. Now, it doesn't tell me the value of c, though. It just tells me the value of x. But like we just went over, we can just apply the vertex analysis and take that value of x and plug it into the equation f of x, and then we can see for what value of c would give me 0 there. Let me show you that last part just to wrap up the video. Okay, so setting df dx equal to 0 told me to use x is equal to k over 2. Okay? But remember that if I'm going to go this route, for some reason the video just stopped recording, so I was right here where I had just solved for x is equal to k over 2, but because it's shut off, I thought I would take a moment to kind of explain what I was doing, so hopefully you didn't feel too lost. The first thing I want to say is that this is my third method to find the same bifurcation value that I found first algebraically using the quadratic formula, and second, I did it geometrically by locating the vertex. So you don't necessarily need this method, but I think it's just interesting to know that there is this other method too, and I have used it quite a bit in practice for those who are thinking about moving on to more advanced topics. So in this third method, the logic is that bifurcations are going to occur where we have a point of horizontal tangency in the value of df dx. Okay, and that's usually where we would see a double root or something happen, just like when we pull this parabola down and we see the double root occur in the case of this dotted line. Okay, so to go through the algebra, the steps are, for this third method, that you're going to set df dx equal to 0. That's the place that's going to locate the horizontal tangent for you. And you're going to solve those for the value of x star that's going to make that happen. But remember that x star is only going to be a fixed point if f of x star is equal to 0, right? So you also have to so you're forcing two things at the same time. First, you're asking there to be a horizontal tangent, and secondly, you're asking that that horizontal tangent occur right here at a root, okay? So this part where we ended before it got cut off is the part that told me what value of x would make me have a horizontal tangent. But I can't have the horizontal tangent occurring up here. I need it to be occurring, like in this dotted case, right at the root. So I need it to be happening at the same time that f of that is equal to 0. And so that's the second step that we're going to go to now. And then you would solve that statement that I'm going to write down right here for your parameter of interest. And that would give you the bifurcation value for that parameter of interest, which in our case is the parameter c, the harvesting rate. Okay, so now I'm going to take this value, x is equal to k over 2, that I found by setting df dx equal to 0, and I'm going to plug it into my equation f of x, and I'm going to get an expression for f of k over 2. Remember, f of x is the equation, the logistic model with harvesting that I had up on the board before, and that equation is r times x, and remember I'm plugging in k over 2 for x, and then it's 1 minus x, which is k over 2 here, divided by k, minus c, and I want to force that to equal 0. You see, so I'm taking that and I'm plugging that in for x, and then I'm saying I want that to be 0, which is the same thing as saying I want this red horizontal tangent to occur at the location of a root. So I'm looking for this to happen, horizontal tangent and being a root at the same time. This is probably the most complicated way to find the bifurcation value, but it's also the most general. So that's why I'm saying it will be of interest to people who want to take their knowledge of bifurcation further into more advanced settings. Okay, so simplifying this equation out gives us r times k over 2 times these k's cancel, so you get 1/2 here minus c. And so that's equal, I want that to be equal to 0. And so I end up having rk over 4 minus c equals 0. And so the same conclusion I reached before is that c needs to be rk over 4. Okay? So again, just to review this final method, the thing that I got here, the fact that x is equal to k over 2, I got that by setting df dx equal to 0. And the second thing I got, where this is the parameter that guarantees that that's a fixed point, is by setting f of x. I got this part by setting f of x equal to 0 using the value of x that I obtained from the first step. Okay, that's a little complicated, but hopefully some people appreciate it. Definitely use that method myself many times to find a bifurcation value.